Ready. Okay, so let's get started. We're talking about a famous method called linear least squares. So let's get back to it. And again, I think it's important to reiterate this, and I'll keep reiterating it over and over and over again in this course, that the very first thing that you need to do is to define the problem, right? And our problem right now is to understand what early visual cortex does in humans, right, or in the mammalian system. And we have looked into the neuroscience data, and we have discovered that some of these early cells seem to detect edges in images, and therefore we design edge detectors, right? So what we do is we define the problem. Then we made a hypothesis of what we think a solution to that problem is, or how we can solve that problem. And then we find a mathematical solution to solve that problem, right? Or to use those hypotheses to define a method that solves or addresses the problem. So that was our first assumption, that the early visual cortex does edge detection. Then we moved on to another hypothesis, which is that it extracts points of interest, fiducial points, that can be used for matching different images, or a sequence of images or objects in different images, or edges or unions in different images, right? And that led us to the space scale theory and the definition of SIFT. Right? And again, we derive specific mathematical tools, or we use, rather, known mathematical tools that we know that it's in our arsenal to define methods, algorithms, meaning that solve that problem, correct? Now, for the next assumption, before we talk about this, we need to review certain basic knowledge of math, meaning linear least squares, and then a few other things that we'll be reviewing to discuss other alternative of what early visual cortex does and why that can be useful to design computer vision systems, okay? So remember, the big picture of the classical model of computer vision systems is that you do low-level vision, then you use the features or information that you extract in these low-level processes from the image. You structure them in a useful way, usually in some fancy space or some shape or texture descriptor that we'll talk about, or even 3D model, and then we use those models to do recognition in high-level vision, right? So that's the process we're going through. Okay. So with all this, let's get back to least squares. So we had already done a lot of derivations. I'll typically just write LS for short from now on, because just faster. So we had already derived a lot of, most of the important components of linear least squares, but in particular, let me note these things. We had a system of equations, right? That is A1, X11, plus A2, X12 plus, and so on, all the way to AP, X1P equals D. And then, so this is our general equation, and we have n such equations. So I have A1 xn1 plus A2 xn2 plus all the way to AP x and p equals d. That is our system of equations. What we did next, we actually wrote this in matrix form, right? Which you'll remember from 5460 that we spent a lot of time describing how can we write things in matrix form, because then we can use linear algebra, we can use statistics, analysis of tensors that we can use, that we know how to use, and that's very useful to us. So we define a matrix capital X whose rows, so I'm going to write this as X1 transpose, right, meaning the row vector through Xn transpose, right? Where each of these xi's correspond, so with xi transpose equal to xi1 through xi p, right? That was the dimensionality. And let's assume for the sake of discussion for now that they're in the real domain. They could be in the complex domain as well, or even in SP, the surface of a hypersphere. We'll briefly talk about all this, but for now let's assume that this vector is in the real domain to make things easier on us. And then, so that is all the vectors, the observations that we have, and then we have our vector A of unknowns, which is A1, A2 through AP. And again, this is just a vector in p dimensions, right? P-dimensional space. And then we did derivations. Least squares basically means that for now we assume, let's assume, I'll come back to this in a second, that d is equal to 0. We'll come back to this in a second and show the result when d is not 0, right? But for now, let's assume d is equal to 0. So these are homogeneous equations, okay? And then in that case, what does least squares do? Well, we take the square of this product multiplication, right? Which is the same as adding all these different equations together and equaling this to a value, right? And we want to basically minimize this and want to make this value, let's call it lambda, as small as possible, right? And we know that xa square is nothing else than A transpose X transpose, right? So we interchange those, we transpose them, and then XA. And we call that matrix Q, I believe. And this is by definition a symmetric matrix, right? Because this is X transpose X. So by definition, I'm just multiplying the rows or the columns, right? I'm making these columns now with themselves, right? So obviously this is a symmetric matrix. And it's positive defined. Anything, in fact, that's squared, it's positive defined, right? And to be precise, we should say positive semi-defined because it could be 0 if they are all 0 values, but it's either semi-defined or positive defined. And so what we have is this solution, right? So what we need to find is we need to find the argument A that minimizes A transpose X transpose, Q. I'll write define Q. So QA, right? That's what we want to do. And we know that this is equal to this value lambda, right? Now, this is if we only look for a value A. We also said that we can look for multiple solutions, right? So I call capital A, A1 through AP, all the different possible solutions that I can find using this equation, in which case then this equation, right, corresponds to A transpose QA equal capital lambda, where now capital lambda, it's a diagonal matrix of solutions, right? So lambda 1 through lambda p, right? So for A, I only get one solution, right? Whatever the error, remember we call this the error because this has, if you have more equations, if n is larger than p, then there are no solutions, right? Right, we define this, remember? And then we define this as the error, right? So this is the error of finding the solution for the vector A, right? That minimizes that value here, right? Okay. Any questions? So far, so good. I mean, we did this in 5460 in detail. If you haven't taken 5460 here, please do go online in the video lectures on YouTube and just watch them, those sections. And also, I went into much greater detail in my course, Machine Learning, which is also on YouTube. And if you're still here next year, well, you can take it next year when it be offered. Okay? So this is where we were. And I don't know if I say this, but this is called the shared decomposition, famous decomposition. And because we know that A transpose A is equal to the identity matrix, because I'm going to make these solutions orthogonal to one another, I can also rewrite this. So if, or not do if, since A transpose A is equal to the identity matrix, then I can write this solution as QA, this is Q capital A, equals lambda A capital lambda, right? And that's our solution here. And we know what this is. This is the generalized eigenvalue decomposition problem that you all know. So generalized eigenvalue decomposition problem, right? And there are functions in MATLAB, right, like Ix, and lots of libraries for C, C++, Python, you name it, that have functions that give you the eigenvectors and eigenvalues, right? And here the eigenvectors are the columns of the matrix A, correspond to the eigenvectors, and therefore those columns correspond to the solutions, the AIs that I'm looking for, right? And the corresponding eigenvalues correspond to these errors that we are associating to each of these solutions, right? So A1 through AP are possible solutions. Okay, that's odd. Better. Possible solutions to our original problem, right? And which, remember, it's solving this system of equations. That's our problem, right? And lambda 1 through lambda p are the corresponding errors associated to each AI, right? Make sense? Now, you have to order the eigenvectors and eigenvalues somehow. I think I said, I don't know if I said this last time, but if not, I usually order them from largest to smallest, which means that I would write lambda p as the smallest, which must be equal or larger than 0, because this is positive semi-definite, right? Q. If it's positive semi-definite, then there might be, or there will be, a lambda that is equal to 0, right? Because it's going to be null space of Q. But if it's positive definite, which is pretty common, then this will be larger than 0, right? There's not going to be a solution. Come? Now, if n is larger than p, and we'll talk about this later on, then that matrix is going to be, it's not going to be full rank, right? So there's going to be solutions that, actually infinite solutions probably, that are going to give me a 0 error. So we'll talk about how to solve all these different things. Okay. let's see, what else? OK, so what I want to do then is to, for my problem, right? What's my problem? My problem is to find the unknowns. And the unknowns are these parameters here, right? So these are my unknowns. Right? And I want to find what are the best unknowns here, right? The best values for A1 through AP, such that when I use them here in this equation, this value is the minimum possible value I can ever get, right? And which one is it going to be? It's going to be AP, because that's going to give me lambda p, which is the smallest possible value ever I can ever obtain in the system of equations, right? So our solution, right, for our problem, so the solution to our problem is to assign A, the vector A, equals AP from here, right? So the eigenvector, so let's say i.e. the eigenvector associated to the smallest eigenvalue. Right? And this thing here, obviously, this is the least square solution. OK? Now we are almost done, but we are not done. Right? Now remember, I see you all taking pictures. Remember, there are going to be plenty of slides online with all the equations. You're welcome to take pictures, but just to remind you. So we're almost done, but we're not done yet, because we had an assumption that d was equal to 0, and that may not be, right? So what happens when d is not 0? So let's solve for that problem. So here, what if d is different than 0? So in that case, what we have is a slight different equation. So remember the error, we define the error square as the sum from 1 through n, all of our different equations of the sum of equations. Now for simplicity, let me assume that my equations are just two-dimensional, right? So I only have A1 and A2, and we'll extend it to AP, A1 through AP in a second. But it's just easier to draw the equations on the board, right? So I'm going to have A1 xi1 plus A2 xi2 minus d, right, squared. Right? So that's exactly the same as this system of equations right here, where I've moved d to the other side, right? That's negative d. Make sense? OK. So I want to find the minimum, the value of a that gives me the minimum value for r squared, right? How can I do this? Well, we know of a method to do that. We can take the partial derivative of this equation with respect to the parameters. And which is the new parameter I have? D, right? I don't have solution for d. So let's take the partial derivative of r squared with respect to d and equal this to 0. And we know that the partial derivative is the gradient of the solution, right? And at the minimum, right, at the value where r squared is minimum, that value is going to be 0, right, the partial derivative. So that's what I want to find. So let's do this. The partial derivative with respect to d. OK. And this would be equal to, this is a 2, so I'm going to move it here, right? 2 times the sum of everything in here, which is A1 xi1 plus A2 xi2 minus d, times the derivative of the inside, which is 0, 0, negative 1. So I'm just going to put the negative in front, right? Yeah? OK. So that's my partial derivative. easy enough. Now I'm going to rearrange these terms. What I'm going to do, I'm going to write now from here, I can write D is equal to A1 times mu1 plus A2 times mu2, where mu j it's equal to n inverse, or 1 over n, the sum of j from 1 to n of xij. So meaning I'm just taking the average value of my xij's, right? And now with this, so this I just obtained it from here, from this equation. And now substituting this over here, right? So this gives me this. And now I substitute this over here. And what do I obtain? I obtain r squared is equal to the sum from 1 through n of a1 xi1 minus mu1 plus a2 xi2 minus mu2, right? Right? So this corresponds to now, because this, right, from here, I can get the average, right? So I'm just getting the average of every xij here, right, into the mu i's. And then I take a1 mu1 and a2 mu2, right, from here. And now I substitute this value here into D, and I have a1, and it's xi1 minus mu1, right? And the same for 2, right? Make sense? Okay, so now let's write it in matrix form, because we just love matrix form. So if I write the same result in matrix form, I'm going to get the following result. So if I write this in matrix form, I'm going to have a matrix UA equals 0, where the matrix U right, A, it's the same vector that I had before. The vector of unknowns hasn't changed. A1, A2, in the general case, A1 through AP, right? And the matrix U now, it's going to be the course what used to be xi's now, but it's going to be the xi1 minus a mu1 and the xi2 minus a mu2, right? So I'm just going to write this here. This is going to be x11 for I equal to 1 is x11 minus mu1 and x12 minus mu2, right? Correct? And this is going to be the same, x21 mu1, x22 mu2, and all the way to xn1 minus mu1 and xn2 minus mu2. Yes, right? Yes? So that's the same equation as I have there, but in matrix form. And to do list of squares, what do? We square this, correct? And if I square this is the same as computing A transpose U transpose UA, right? So now I want to compute this matrix, a symmetric positive semi-definite matrix U transpose U, same as I did before. And I'll leave this as an exercise at this point. You can just keep repeating this, right? So practice at home, just doing these different steps. And if you do that, you're going to get a matrix which is called sigma x, which is equal to, let's see, I'm going to give you a couple of steps so that way when you do it at home, you can practice. So the very first thing that you're going to get, it's the sum from 1 through n of xi1 square minus n times mu1 square. The same here in the other diagonal. The sum from 1 through n. But now in that case, is instead of I1, it's going to be I2 square minus n mu2 square. And then in the off diagonals, you're going to have x1 and x2. So you're going to have the sum here from 1 through n of xi1, xi2 minus n mu1, mu2, right? And that's easy to see because this is U transpose U, so you just transpose this and you multiply this by itself, right, versus this by this other one, right? Okay. And the same thing here in this other diagonal. You have the sum from 1 through n of xi1, xi2 minus n mu1, mu2. And you can rewrite this as in a more common form, which is the sum from 1 through n of xi1 minus mu1 square, the sum from 1 through n of xi1 minus mu1 times xi2 minus mu2. And here, the same summation term of the same thing as this, xi1 minus mu1, xi2 minus mu2. And here, it's exactly the same as this, but for mu2 and xi2, right? Same thing. So the sum of 1 through n, xi2 minus mu2. Okay? All right, so almost done. So now we have our matrix, sigma x. And as we did before, that's going to give us our solution, our least square solution. And usually you can write sigma x from here, from this matrix that we have derived here. You can write it as follows. Sigma x is equal to the sum from 1 through n of xi minus mu times xi minus mu transpose, right? Whereas before, right, xi, it's our vector, right, of xi1 through xip. And therefore, I just generalize it from 2 to p right now, right? I could have written x1 and x2 as I have done, or I can just write it for all my p's. And I have the generalization here that I'm looking for. And mu, in that case, is equal to mu1 through mu p, right? So what's our least square solution, as we had done before? Our least square solution is finding the eigenvector associated to the smallest eigenvalue of sigma x, right? So let's write this down. So the eigenvector, we've called it AP, associated to the smallest eigenvalue, we call it lambda p, right, of sigma x. So all we need to do is just do an eigenvalue decomposition of sigma x, and we're done, right? And that's the beauty of linear least squares. The beauty of linear least squares is that if you can set out a system of equations, you write it in matrix form, you compute what is the matrix. In that case, that's a matrix, sigma x, right, that you need to compute the solution for, and then a simple eigenvalue decomposition gives you this solution. It's perfect. It's beautiful, right? Very efficient, very simple. Now, I do want to mention very quickly, I'm not going to talk about this, but I do want to mention that computing the eigenvectors and the eigenvalues of a matrix like sigma x, it's non-trivial, right? And There are many optimization, many efficient optimization algorithms that exist out there to do that. If you're interested, I do cover this very little, but a little in machine learning. But if you really want to learn this, then you have to take optimization, right? In optimization, they'll teach you how to define algorithms to compute things like eigenvalues and eigenvectors, right? So, for example, the classical solution for the eigenvalue decomposition problem is to finding the Lagrange multiplier of a system of equations, right? That's still easier said than done because there are many optimization problems that you have to deal with. So people have defined algorithms over the years, like the Jacobi, the QR algorithms. There are efficient ways of trying to find these eigenvectors. One of the reasons this becomes difficult is because the size of these matrices can be huge, right? Because the number of equations that we may end up with, and as we'll see in computer vision, or the dimensionality P of our space, which could be the number of features. Say, I could extract a feature per pixel. I could extract even 100 features per pixel, right? And if I have an image of 10 million pixels, I may end up with hundreds of millions, if not billions of dimensions. It's absolutely huge matrices. There's absolutely a tremendous number of problems that we need to address and that we will address as time comes, right? But this is the basic concept that we need to know for now on how to solve this problem. So this, you have to tattoo it in your brain one way or another, because you will be using, if you want to work in computer vision, machine learning, image processing, even other areas of AI, you will be using linear least squares all the time. There's just no way around that, okay? All right, any questions? Nope? Sure? Okay, this matrix, sigma x here, it's called the covariance matrix. Very famous matrix. And it turns out, I'm just going to make this as a parenthesis, as a comment. We will use it briefly, but it's not one of the things we'll be using the most. But it's interesting to note that you can factor out that matrix into two components. One matrix we're going to call gamma, and another matrix R. And I'm going to factor this out as gamma R gamma, okay? Where this matrix gamma is equal to a diagonal matrix of the variances, sigma 1 through sigma p, and zeros in the off diagonal. So just a diagonal matrix of the variances. And R is a matrix with ones in the diagonal. And in the off diagonals, these row values. Let's call it row 1, 2. So all these are zeros here. Row 1, 2 through row 1p. And here I'm going to say row 1p through row there'll be 2, so there's going to be p minus 1 or n minus 1 p. Okay? And the last one, it's a 1. Okay? And what are these rows? So these are easy to understand, right? These are the variances. So these define the variance. And that's easy to understand because from here, or even better from here, right, we can see that the diagonals actually define the square of the variance, right? I mean, that's what that equation does, right? Now, I haven't shown you here all the details. Usually, this equation is normalized by either the number of samples or the number of samples minus 1. Again, these are details that I'm going to skip for now because we'll talk about this to make this equation nicer, to make it work, to make everything work very nice. But in any regard, this allows you to compute the variances that you have over there, the square, and then you're left with these other values out here. And these other values in the off-diagonal of the covariance matrix define the actual correlations that we started this discussion with. So remember that I said we're interested to know how correlated each of the two dimensions of my feature space, x1, x2, x3, x4, and so on, how correlated these dimensions are, right? Well, those are the correlations. These rows actually tell you how correlated 1 and 2 are. So row 1, 2 is a correlation between the first dimension and the second dimension of your feature space, right? Row 1, 3, the correlation between the first and the third dimension. Row 1, 4, between the first and the fourth, and so on, right? So in general, row ij will tell you the correlation between the ith and the jth dimension of your feature space. So this is really cool. So when we get to high-level vision, one way that you can define an algorithm to recognize objects is by looking at these correlations in your feature space, right? So for example, you could extract as features in many locations, for example, in some corners, wherever you have corners in the image, right? So you use the Harris corner detector to detect corners in the image. And in those positions, you extract Gabor, or you do convolutions with Gabor filters, right? In these locations at certain scales, meaning certain window sizes for the kernel, right? And then each of these Gabors that you use in these local corner detections, it's going to define the dimension of your feature space, right? And then what you're going to look for, you're going to look for the correlations. When I do this with images of tables, I'm going to see certain number of correlations here. And when I do it for chairs or for cars, I'm going to find some other correlations. And those correlations allow me to distinguish whether I'm looking at a chair, a table, or a car. Okay? So you can already start seeing where all this is going in this structure of the classical model of computer vision. Okay, awesome. Any questions? Yes, please.
For the R matrix in the bottom right, does that go up to P of P minus 1? Or
The PP. Right, yes. Well, so because the diagonals are ones, right?
Mm-hmm.
Yes, exactly.
Okay.
So you're going to go through 1p all the way to 1p minus 1 and then a 1, right? Yeah? Yes.
Whether in the left part of the matrix, there should be xi2 minus mu2 squared.
Ah, yes. Thank you. Yes, there's a missing square here. Excellent. Yes, indeed. All right. Good job. What else? Are we good? All right, so that's linear least squares. We're going to use it constantly all the time. Of course, we're going to use many other tools. This is not image processing or introduction to image processing and computer vision, where we almost only use linear least squares. But we're going to use a variety of tools, but this is going to be one of our main tools. But this tool now, it's going to allow us to define or to work with a new hypothesis of what early visual cortex actually does in the mammalian visual system, right? In human vision and mammals in general. Okay, so let's see that. Let's make some space here. And let's go back to our basic model of the brain. Now remember, we have something like this, right? This is a side view of the brain, right? I mean, approximately. So we have the eye bulb here, right? We receive vision from the outside world where there is an object. Maybe that's my object right here, right? All right, what do you think? Okay, our object, right? And there is a projection of that object in the back of the retina, and then that is projected through some subcortical areas here, the LGN primarily, and then that goes to V1 and then V2, right? Toward this pathway, the ventral pathway, right? There's another pathway which is over here, we'll talk about later. But for now, let's focus on the ventral pathway. Okay, so we have looked at the neuroscience literature, and it turns out that the cells, even in the retina, especially LGN and early visual cortex, they either seem to be detecting edges or some types of unions or maybe some Gabor filtering, right? There's another hypothesis, and the hypothesis is that early visual cortex is trying to, well, not only early visual cortex, but in general, our visual system is trying to obtain or discover what are the causes of the image, what are the elements that have caused our observation. Because let's face it, our observation, what we observe from the world, is not the real world. It's just an image of what it's out there, right? And it's even more complicated than this, obviously, because the 3D world that we live in is not painted in colors, right? Obviously, that would be absurd. What happens is that there is the light actually vibrates, or there's a frequency at the range of values, right? And depending on the range, you have gamma rays, or you have ultraviolet, or you have the visual spectrum, or you go into infrareds, and you have X-rays, and you have all these varieties of bands, right, of depending on the frequency. We have sensors in our retina that are only able to capture the light that has a specific frequency, right? This light is nothing else than an electromagnetic wave. It has a frequency. The one has frequency that we call the visual spectrum, because it's what we can see, right? And if it vibrates in this small portion of the visual spectrum, we call it blue. And if it vibrates in this other middle area, we call it green. And if it vibrates here, we call it red, and what have you, right? But we call it like this. It's not that it's painted like this in the real world. It's something, not only this, but everything else works like this. The real world is following the laws of physics, and our biological system has adapted to extract some useful information from the world to help us interpret it, right? So with computer vision and cameras, we have to do exactly the same. We have to find ways of extracting the reality of the world, so the causes of what the world is like. Okay, so maybe the goal of early visual cortex is in fact, or the early visual cortex is in fact tasked to extract these causal relationships, and the model that we'll usually be working with, not exclusively, but we'll usually be working with, it's a simple, very simple linear model. We'll have x. X is our observation, like our image. That's what we observe. It's equal to a matrix A multiplied by S. S is the actual sources, what I actually have in the real world, plus some noise. Okay? That's a very simple linear model. Okay? This is, again, this is our observation. These are the sources. This is what we're really interested in. The sources are what we really want to find out, right? What's out there. But we don't see the sources. We see X. This is called the mixing matrix. And it's just a noise vector. OK? Very simple model. So our goal is to find S given X. That's our goal. So I could write this hypothesis as follows. The brain is trying to reformat. And by the brain, I could change this for early vision, right, if you prefer, is trying to reformat the incoming information, in hopes, right, of finding the underlying causes. The underlying, I would say probably, but unknown, right? Unknown causes in the world, right? Or of the world. Let's just leave it at that. The underlying causes. The ones that have caused the image or that are responsible for constructing or creating the image. OK? So under this hypothesis, what does early visual cortex do? It just tries to solve the system of equations here, right? Problem is, we don't know what S is, right? What's the dimensionality of S? S is, say, in the real domain of Q dimensions. This is in P dimensions. And this, we have no idea what the noise is, right? And you'll see in computer vision where people usually say in their algorithms, we assume Gaussian noise, right? What they mean by Gaussian noise is that in a model like this is distributed according to a Gaussian distribution, right? And it's very common to assume that it's zero mean, that Gaussian is zero mean, and maybe a fixed variance, right? Unit variance. So you will read in the papers and in the literature, you'll read, we assume zero mean, unit variance, Gaussian noise. And that's what they mean, right? And the reason this is done is because otherwise the equations become too difficult to solve. OK? All right. So here's what we're going to do to test this or to explore this hypothesis. We're going to start with images, right? So we're going to start with a set of images. Not just one, but a set of them. OK? So this is my set of images. Let's call it M images. Now, for each of these images, OK, let me do that a little better. There we go. Okay. For each of these images, what we're going to do is we are going to extract information from some small local area, from a window. Okay? And that we're going to write it as a vector x that we're going to assume it's in some space of p dimensions. Okay? And that window, we're going to extract that window in multiple places in each image. Okay? Just for simplicity, you can do it randomly. You'll actually be doing this in a project, so it's good to understand what that means. You could do it in a grid, or you could just do it randomly. Doesn't matter. Okay? But you extract multiple windows of some size, right, of, say, p by p, or which in case would be p squared here, right, or whatever it is, right, but some size that is fixed. And you extract this throughout all the images that you have here, okay, all of them. So far, so good. And that gives you a set of smaller images. So let's write this down. So this will give you a set of windows right? So the first window that corresponds to the first window in the first image, the second window in the first image, and so on, up to the last window in the first image. And then you repeat that for every other image, right? And you obtain, if I extract 10 windows in 100 images, I have 1,000 such windows, right? Generally, you obtain many, many more, right? Thousands, tens of thousands, hundreds of thousands. And now these are going to be our xi's, right? x1, x2, all the way to xn. Okay? And our number of windows that we have extracted. And each of them, remember, each xi is defined in some space of p dimensions, or p squared if you consider p by p pixels. Okay? So far, so good? Okay. And now we want to find the common factors that define these windows. Where are the common factors that define these windows? So how can we do that? Well, we write down the equations, right? We write down the equations where now our parameters are the parameters that are going to best describe each of these windows that I have, right? And we already know how to do that, right? We write down the equations, right? We compute the solution using the covariance matrix, right? We compute the covariance matrix of our observations, xi's minus the mui's, right? We have the covariance matrix, and we compute the eigenvectors and eigenvalues, right? So from here, we compute sigma x, right, to find the underlying causes of these images, or rather than these images, let's say this image set. Okay? The S's that we're looking for in that model, right? And the least square solution to that, the LS solution to this, is going to be the eigenvectors and eigenvalues of sigma x, right? Now remember that we've already discussed this. How do you define xi? Well, you take that window and you take the pixels in that window, right? The first pixel of that window corresponds to the first position of x1, so x11. The second pixel becomes x12, the third pixel x13, and so on, right? And usually when you finish the first row, you go to the left-hand side of the second row. But it doesn't matter which pattern you follow, as long as you follow always the same pattern. Okay? Okay, and the reason I remind you of this is because now our solutions are going to be the eigenvectors, E1, actually we call them A1 through AP before, right? These are my eigenvectors. And I can actually visualize these eigenvectors, right? Because I can do the inverse process of this. Remember when I transformed an image, right? A two-dimensional tensor, two-order tensor, to a one-order tensor, right? From a matrix to a vector. Now I can go back with the inverse function, right? Again, there's a function in MATLAB, it's called reshape, right? It just reshapes it automatically to whatever you want, right? So you can actually convert that vector into an image again, and if you do that with x1, you end up with the original image. But my question is not what this original image looks like, but what have we recovered here, these S's, right? These underlying sources that we are looking for. What does this look like? And to do that, we have to visualize these eigenvectors. So let's do that. OK, let's see. Can I? There we go. All right. So there we go. So if you do this, right, so you take images, you extract windows. As I said, it could be like this in a grid. It could be random. That's irrelevant, right? And then you compute the covariance matrix, and you extract the eigenvectors, and you visualize the eigenvectors. These are the eigenvectors that you obtain. So according to the least squares solution, these are the causes, the basic causes that generate images, or the basis vectors, right, that allow you to generate images. Now, do you remember when in 5460 we spent some time talking about image compression? In image compression, what we were trying to find is basis vectors of some space that allow us to reconstruct every possible image, right? That's exactly the same. That's exactly the same thing that we're doing here. These are the basis vectors, right, that allow us to construct every possible window of a natural image, a natural scene like this, right? And note that these actually look like edges. Some of them look like some sinusoidal functions like DCT-bases, right? Some of them look like derivatives of Gaussians, maybe to some extent some Gabors. They look actually very interesting, right? So the idea then becomes that maybe early visual cortex is only interested in finding these basis vectors, right, these S's in that model that I've talked about, to represent the incoming images in a space that is useful for mid-level and high-level vision to perform its tasks. Okay? And we'll spend quite a bit of time talking about how to use these representations to do high-level vision. Okay? So far, so good? Okay. Now, there is more. So let me turn that off if I can for a second. Okay. While I wait for the lights to turn on, let me probably erase this. So it's going to be part of the next project, everything that we've covered in today's lecture, because this is going to be fundamental to do a lot of the work that we're going to be doing later on. Okay. Wow, that's slow. Okay, so let's move on without the lights while we wait for the lights. Another way to look into this, so this is the least squares solution, right? Now remember, I've made a hypothesis and I create a model, right, based on this linear combination of sources. And then I've used linear least squares to find a solution, right, to that problem. But linear least squares is not the only possible solution, right? There's another solution that's using some type of nonlinear correlations, which if we had time to cover this, which I don't, but again, machine learning would be a course to get to learn this, or estimation theory, which is another course that we have in the department. They'll give you nonlinear correlations would be associated with independent basis vectors for the SIs. So you're looking for independence in the SIs, okay? And one way to describe this is in this model where I have, say, the image. Maybe I can say image X for a specific patch of the image that I have described. It's the sum from 1 through m of ai, some basis vector phi I of x plus my noise vector epsilon x, right? Some noise. And these underlying features, right? This one's here. These underlying features that I'm trying to get to. There we go. These underlying features that I'm trying to find now, I want them to be as independent as possible. One way to solve this problem is to maximize the sparsity. So we want this representation to be sparse, meaning that these AIs that I have there, I want them to be mostly zeros, and once in a while, a 1, right? And why do I want this? So here is the underlying idea of this. What I want is a specific basis vectors, these phi i's, right? That when I have a window, I only need a very small number of them to regenerate that image. Now in least squares, that doesn't happen, does it? Because in least squares, because we eliminate correlated dimensions, what happens is actually the opposite. Each basis vector is very important to reconstruct every single image. Here is the opposite, right? We want the basis vectors, a small number of basis vectors, to be sufficient to represent each image patch. Okay? So it's actually almost the opposite of the original solution. And with that, for that, we can maximize the sparsity of our coefficients A. So that means that we have to redefine our error function. And for example, I could define my error function E as 1/2 of I minus rho A square plus lambda. Actually, let me just do one step at a time. Let's do this first step. This 1/2, don't worry about it. This is just for what's called mathematical convenience. And the reason is that once you start taking derivatives of this, this 2 and that 2 cancel out, and it's easier to implement. It's just a constant, it's irrelevant, okay? So What does this do? This says this phi, right? This is capital phi now. It's the set of all my phi 1s through phi, what did I say? M, right? Okay, so it's a matrix whose columns now, or rows, depending on how you build this, right, correspond to the basis vectors. Okay, in that case, it would be the rows because I have A on the other side. Okay. Okay. And what I want is to minimize that error. And what's that error? That error is a very classical error function, a very classical criterion that you'll see in computer vision that is called the reconstruction error. You want to make sure that you find some basis vectors, phi here, that can reconstruct the image I as closely as possible for all the images that I have, right? So we're going to do that for all the images. So I want to be able to reconstruct my image as accurately as possible with certain set of basis vectors. This is, again, called image reconstruction or reconstruction error. Error criterion, etc. Very, very common criterion. And so far so good. We haven't specified sparsity now, so we need to add to that criterion that we're defining some sparsity function. Let's call it C of AI, where Ci, it's a function that maximizes a function that maximizes sparseness. Okay? And I'm going to multiply this by some value, say alpha. Okay. And this term here, we are going to refer to it as a regularizer. And the reason for this is because this second component here, for some small alpha, is going to regularize the value of this reconstruction criterion or whatever other criterion that I have. Okay? And this is something extremely typical in computer vision and machine learning, where we define a criterion and we regularize it to find a specific solution that is convenient for us. Okay. So I have, as I said, capital phi are phi 1 through phi m. And I have a vector now A, which is A1 through AM as well, right? And now I have my function C, which measures is a function that measures sparseness. Okay. Now, I posted a paper that did this years ago. I posted that in Canvas. And in that paper, for this function C, they use nonlinear functions. They use C of x equals to negative the exponential of negative x squared, or the log of 1 plus x squared, or the absolute value of x, right? Nonlinear functions like this. Another way to do this, so this is one way of computing a sparseness. Another way, very common to do this, is by specifying a norm for your vector x, right? So, for example, there is the so-called zero norm, which is a really wrong. It's actually the wrong name for that norm because the zero norm is not a norm by definition. But at any rate, that counts the number of elements or entries in your vector. They're different than 0. That's it, right? And obviously, if you want to minimize that, then the smaller number of elements, that are different than 0, the smaller the norm, and therefore you're maximizing sparsity, right? There is another norm called the nuclear norm that people also like to use. You could also use quasi-norms. Remember from 5460, these are norms like the p norm with p values smaller than 1 but larger than 0. Okay, all those are called quasi-norms. Okay, so I posted this paper in Canvas, and I just want to show you very quickly what the result of this is when you apply this to the images that we have described before. So these results that you have in the slides, use the exact same method that I've shown for the least square solution, right? So you start with these images of natural images. There it is, right? Start with these natural images. You extract certain windows in each image. You put these images together, and then instead of using the least square solution on all these vectors that define these windows, use this new solution for sparseness, right? And the result that you obtain is something like this. And I mean, you have to now tell me if this is not interesting. These are almost Gabor filters. So it turns out that extracting sparse basis vectors from natural images, from windows of natural images, gives you pretty much Gabor filters, which, remember, is what neuroscientists found to be found the cells of early visual cortex to be doing, to be filtering like Gabor filters. So maybe that hypothesis isn't that crazy, that the early visual cortex task is actually to extract a sparse basis vectors that can reconstruct the image, because those are fundamental underlying properties of the image that can be then very efficiently used to do mid-level vision and high-level vision. Okay? Now with that, something else pops up, which is note that you're actually, you can start representing this image, every image that you have, with a very large number of basis vectors, right? Huge number of basis vectors. That is called an over-representation, right? Because you are now representing the image with more information that you started with. So instead of actually compressing the image like we do it in 5460 in image compression, finding the smallest number of eigenvectors, right, the least square solution to represent the image so I can actually compress it, now you're actually expanding the representation. You're making it as large as possible, larger than the original representation. Why? Because it's in a sparse representation, right? And a few number of them are useful for reconstructing some images, but a small number of other basis vectors are used for other images, right? So might that be useful? Maybe we'll get to that later on when we talk about high-level vision. All right, I'll see you Thursday.